Assalamualaikum and selamat sejahtera. In this video, we will focus on specific characteristics of diode, thyristor, and transistors. We will start our discussion with the simplest power switches, which are diodes. Unlike other power switches covered in this topic, diodes are uncontrollable devices. Thus, we cannot control their operation. A diode will switch from off state to on state and vice versa depends on the nature of the current flow in electrical circuits. If the current flows toward the anode terminal, the diode is in forward bias and it will turn on. According to the VI characteristic curve, in this condition, the diode can conduct high current from anode to cathode with a small voltage drop. However, when the current flows toward the cathode terminal, the diode is in reverse bias and it will turn off. From the curve, we can see that the diode in this condition will block very high voltage with small leakage current. This characteristic is valid as long as the block voltage does not exceed the reverse breakdown voltage level. These figures show the transient characteristics of diodes. It is referring to a condition when the diodes are switching from on state to off state. When the diodes turn off, the current conducted by the diode decreases until negative values before it becomes zero. The time taken for the current to reach zero is called reverse recovery time or TRR. Based on TRR, there are soft recovery and abrupt recovery. Based on the reverse recovery time, there are several types of diodes. Please check this table. The second power switch is thyristors. As we can see at the symbol, the only difference between thyristors and diodes is the gate terminal. This terminal is important because thyristors are controllable devices. When current flows to the anode terminal, a thyristor is ready to work under forward bias. It can happen when we supply gate or control signal to the gate terminal. The type of the gate signal is a current signal. According to the VI characteristic curve, by applying the gate signal, a thyristor can conduct large current with a small voltage drop. Nevertheless, when the current flows to the cathode terminal, the thyristor works under reverse bias and as a result, it will block high voltage with small leakage current. Next, I will use a simple circuit and output voltage and output current waveforms to demonstrate the operation of a thyristor. To show the difference between the thyristor and a diode, I will start the demonstration with the diode operation. Keep in mind, this demonstration involves ideal power switches only. Hence, there is no leakage current during the off state and no voltage drop during the on state. Firstly, let's look at the circuit diagram. As you can see here, this time I am using an AC voltage source. The equation for the supply voltage is Vm sin omega t, where Vm is the peak amplitude of the voltage waveform. According to this equation, we can have this following waveform. As you learned before, during the positive half cycle of the supply voltage, electric current will flow from the positive terminal of the voltage source. Therefore, the current will flow to the anode terminal of the diode, and as a result, the diode is in forward bias and it will act as a short circuit. Therefore, current can circulate in the circuit through the diode. Since the load is a resistor, hence the wave shape of the output current waveform is following the supply voltage waveform, but with small amplitude. Hence, we can sketch the output current waveform like this. Next, by analyzing the circuit, we can also sketch the output voltage waveform across the resistor. Now, the supply voltage waveform is in the negative half cycle. For this condition, the current will flow from the negative terminal of the voltage source to the cathode terminal of the diode. As a result, the diode is in reverse bias and it will act as an open circuit. Therefore, no current can flow through it and the output voltage is also zero. Based on this information, we can sketch the output voltage and current waveforms like this. Now, I will change the power switch to a thyristor. As explained before, this power switch requires a gate signal to operate. Based on the initial position of the gate signal, we can see that the thyristor is in forward bias when the gate signal is applied during the positive half cycle of the supply voltage. After the gate signal is removed, the thyristor is still in forward bias as long as the supply voltage waveform is positive. Nevertheless, before the gate signal, the thyristor is in reverse bias even though the supply voltage waveform is positive. On the other hand, during the negative half cycle of the supply voltage, we can see the thyristor is in reverse bias although there is a gate signal. Thus, the output voltage and current waveforms are equal to zero. Next, let's see whether the width of the gate signal affects the operation of thyristors. As we can see, after I increase the width of IG, we can see the output voltage and current waveforms on the left side are similar to the right side. Hence, The width of the gate signal does not affect the thyristor's operation. Based on these waveforms, we can say that the operation of thyristors only depends on the starting time of the gate signal. The last power switches to be discussed are transistors. In this topic, we will focus on three types of transistors, which are BJT, MOSFET, and IGBT only. Although there are many types of transistors, their basic operation is quite the same. As similar to thyristors, transistors are also controllable power switches. However, the way to control transistors is different as compared to thyristors. I will use these waveforms to explain the difference. As we can see here, both transistors and thyristors are controlled using the same wave shape of gate signals. Nevertheless, based on this label, we can see that the type of the gate signal can be in the form of a current or voltage signal. It depends on the type of transistors, and I have discussed it in the previous explanation related to the gate signal requirement. Now, let's focus on the regions during the positive half cycle of the supply voltage. Before the gate signals, the color of the region is light blue. It means that both power switches are in reverse bias and turned off. Moreover, based on the color of the regions, we can see that both power switches are also in reverse bias during the negative half cycle of the supply voltage. Based on the gate signals, the wave shape of the output current of the transistor will be like this. Eventually, we can sketch the output wave voltage waveform like this. Based on this waveform, we can see that unlike thyristors, transistors will switch from on state to off state once the gate signal is removed or equal to 0. Hence, we can say that transistors depend fully to the gate signal to remain turned on. Therefore, when we extend the width of the gate signal, we can have these following output voltage and current waveforms. This table shows several characteristics of BJTs, IGBTs, and MOSFETs. You can use this table to compare these transistors in terms of gate signal, current and power capacity, on-state voltage or voltage drop, switching frequency, input impedance and current gain, and also driver complexity. Regarding to the current gain, we can see that only BJTs have low current gain. It is because BJTs are current control devices. As a result, the driver circuit of BJTs is more complicated and it has a higher current rating as compared to IGBTs and MOSFETs. To overcome the complexity of the driver circuit, we can try to increase the current gain. One way to increase the current gain is by using Darlington pair. Please refer to the note or other references to study about the Darlington pair. You can use this VI curve to compare the steady-state characteristics of these three transistors. The y-axis refers to the conducted current and the x-axis is the on-state voltage. To work as a power switch, BJT must work in this region, and for the IGBT, it is this region, and for the MOSFET, it's referring to this region. In this region, as you can see here, the conducted current increases with the increase of gate signal. At the same conducted current, we can see these transistors have different on-state voltage. According to the curve, BJT has the lowest on-state voltage and MOSFET has the highest value. In the middle, it is IGBT. To compare the dynamic state operation of these transistors, you can use this figure. This graph shows the time taken by each transistor to switch from on-state to off-state by observing the conducted current waveforms. According to this graph, the fastest transistor is MOSFET and the slowest is BJT. Once again, IGBT is in the middle. Among all these transistors, IGBTs have been utilized widely in many applications. Meanwhile, the use of MOSFET is restricted to low power application with fast switching frequency. Before I end this video, let's watch a video related to the application of power electronics.
Five, four, three, two, one, zero.
You can use this diagram to choose the suitable power switches for those applications according to their capacity, power capacity, or switching or operation frequency.